Hi everyone. In this video, I'm going to prove the Artin's approximation theorem. This is a very important theorem. It's going to be used a lot throughout the course, but its proof is, quite technical, somewhat, but not too insightful, and it kind of easy to follow. So I decided, because of time constraints, not to prove it in this instantiation of the course during the lectures, but it is important enough that I also don't want to leave it for you to read unguided. So I decided to just record this video, and if you want to see the proof, you can see the proof, and otherwise you can either skip it or read it by yourself. Okay. Okay, so before we begin, I want to discuss something that I kind of omitted in the lectures, which is the kind of absolute value that is induced by evaluation. Because, the approximation theorem has something to do with approximation, and for approximation, you need a sort of distance or metric and so forth. And right, so evaluation actually yields such a thing, and I want to make it more explicit. So it's this part that I kind of skipped somewhere here. So let's go there. Yeah. So let's say we are given a evaluation from the field to some ordered group. And as we'll see throughout essentially the rest of the course, the ordered group that we are going to consider in function fields, and what will become function fields, is Z, or something that's isomorphic to Z. For that particular relation between valuation and absolute value, let's just assume that this is a subgroup of the reals, not necessarily Z. Okay, and now given a non-zero element in the field, let's define this, what's going to be an absolute value. So we're going to use the absolute value symbol, and this function assigned to A, given input A, outputs 2 to the minus the valuation of A. Right, as you may expect, 2 is essentially an arbitrary choice, just you want a number that's larger than 1, so let's just go with 2. The important thing is that it's exponentially decaying with the valuation. And so this is defined for every non-zero element. For the zero element, right, the valuation of 0 is infinity, right? 0 is the only element that is assigned the value 0 by evaluation. And so 2 to minus infinity, so to speak, is 0. And so with this in mind, with this informal discussion, we extend this function by assigning the absolute value of 0 to be equal to 0, as you might expect. Okay, so this is just a function that we have defined, 2 to the minus valuation, or 0 if you are 0. And let's see what we can say about it, given the properties that we know about valuations. So for example, the absolute value, let me just call it absolute value. In a second, it will be an absolute value. We will show it's an absolute value. So the absolute value of the product of A and B, like by definition, is the 2 to the minus the valuation of their product. And because the valuation is a group homomorphism between the multiplicative group of the field and this group, so V of AB is V of A plus V of B. And just because our choice of the way we define the absolute value from the valuation, you can factor this as 2 to the minus the valuation of A times 2 to the minus the valuation of B, which is precisely the absolute value of A times the absolute value of B. So indeed, there is this like well-known expected for property that you would want from an absolute value, which is this multiplicativity. Right, so the additivity here is translated to multiplicativity because we chose the exponential kind of relation there. So what does the triangle inequality says? So it tells you that so let's look at the absolute value of A plus B. And what we want to show is that it is at most the absolute value of A plus the absolute value of B, namely the triangle inequality. And that's essentially the reason why we call this property the triangle inequality for valuations, really. But actually, something stronger is going to happen. So let's see. So the absolute value of A plus B, by definition, is 2 to the minus the valuation of their sum. And by the evaluation triangle inequality, we know that the valuation of the sum is at least the minimum of the individual valuations. And because we have these 2 to the minus, this at least becomes at most when you look at that. Now, like if you think about it for a second, 2 to the minus minimum of V and VB is the maximum of 2 to the minus V and 2 to the minus VB, because 2 to the minus is a decreasing function. And these are this is precisely the maximum between the valuations. So we just showed that the absolute value of a sum is at most not only the sum of the absolute values, but in fact something stronger, the maximum of the absolute values, right? So we established this inequality, which implies the triangle inequality because the maximum is bounded by the sum, right? Everything is non-negative. Okay, so what we've just showed is that a valuation yields, it induces an absolute value, but something actually stronger than an absolute value. And it has a name. So, right. So this notion is called, so if you have an absolute value for which what we have holds, and not just the usual triangle inequality, that's called an Archimedean absolute value. It's a stronger thing, and it is easier to handle. It has more structure. In any case, what we got is an Archimedean absolute value, in particular an absolute value. And because of all of this discussion, you can think of evaluation as measuring closeness, right? It produces an absolute value. So, like if the valuation of an element, so if the valuation of, say, A minus B is large, it means that A and B are close with respect to whatever metric this valuation induces. Okay, and we will see examples in a second. And as you can expect, I mean, once you have this notion of closeness, if you know topology, then it's a good idea to study the topology that is induced by this valuation. But we are not going to do it here. You do it usually when you do algebraic number theory, but we just don't need it here. And the entire philosophy of the course is trying to teach theoretical computer scientists, function fields. So I don't want to, I can't assume like prior knowledge in topology, even though this is very basic. And just as a maybe one remark, I would say that usually when you have an object, like in this case, a function or number or whatever, in our case, this could be a polynomial, and it has a property, maybe it's irreducible or separable and stuff like that, then closeness kind of allows you to say things like, well, if you're close to some polynomial that's separable and irreducible and so forth, maybe you are also kind of inherit these properties. Like there is a notion of continuity of the property. And indeed, that's the case here. So you can show that actually what I said is true. So if you have a function which is separable and irreducible, then functions or polynomials that are close to that also satisfies this property and so on. So that's a direction that you can follow, but we are not going to use it anyhow. So okay, so that is what I owed you about the relation between absolute value and valuations. Let me stress it again. We are not going to use the absolute value point of view of things, but it's a good intuitive tool for you to have. Okay, so with that, let's skip to the unit that I want to talk about, which is Artin's approximation theorem. So let's start. So this unit is about one theorem. It's a very useful theorem, essentially a theorem about interpolation. And it says the following. It says, let's assume you have n valuations, and I'm just going to consider discrete valuations, namely valuations from a field to z. They don't have to be onto, but they are to z. There could be to z. And I'm going to assume that they are non-equivalent. Okay, so kind of you should think of like different points in a sense, like yeah. Oh, sorry, and actually I am assuming for this theorem, I am assuming that I'm taking it back. I am assuming that these are valuations whose image is z, right? You'll see in a second why it is needed. We are not going to need this property for the entire unit, but for the last slide. So I kind of forgot about it. But yeah, we are going to assume all of them are onto. And let's say you're also given n field elements, right? The same number as the valuation that you're given. And n numbers, like prescribed valuation values, really. Okay? Then what I'm saying is that for every choice of n tuple of valuations, non-equivalent valuations, n tuple of functions, and n tuple of prescribed, like numbers, but prescribed valuations could be negative, you can always find a function, like an element x in your field, which you should think of the field of functions, such that with respect to every valuation, every one of the valuations that you have, this x that you found is close to the ith element, and how close? Well, precisely the prescribed value. Okay? So, you can ask why is it called the approximation theorem? You can actually ask why it's called the weak approximation theorem. It sounds quite strong, but you can ask why it's called the approximation theorem. And for that, let's recall the discussion that we just had. Remember that a large valuation corresponds to closeness, right? So saying that x minus ai has valuation according to vi mi is the same thing as saying that the absolute value that is induced by the valuation. So let me denote it by absolute value with a subscript of I here to recall the I valuation is precisely 2 to the minus I. Okay. So that's what I'm saying. I'm saying that you found an element X that is close to the ith element according to the ith metric to the extent that you would want. And as an example, and this example also kind of hints about the relation of this theorem to the Chinese remainder theorem, which you may thought is somewhat relevant. Indeed, so let's say that you want to find a number x, an integer that has residue. It has residue free, when you mod out by 2 to the 5, look at 2 to the 5th, and 10 when you look at 3 to the power 7. Right, so you kind of want to find a number that, like with respect to the 5 p-adic metric to the 2 p-adic matrix is free, but in a sense up to multiplicity 5 and to multiplicity 7 with respect to the third adic valuation. Right, so you can write this like that. You can say that we want v2, this is the 2 adic valuation, of x minus 3 to be at least 5, and v3 of x minus 10 to be at least 7, right? You want to find an element x for which this holds. So that's the way kind of the Artin's approximation theorem is related to the Chinese remainder theorem. Okay. Okay, so the proof of the theorem is kind of long and tedious. It is insightful. It's mostly, essentially an approximation theorem, right? Like an interpolation theorem. You want to find an element that interpolates the right way at different kind of points because the valuation corresponds to points. And it's kind of going to be long. And we're going to have like a 5-step proof, in fact, a 6-step proof, and this is the step number 0. I think we are going to put it in the homework also, so maybe you don't want to look at this part before you do it yourself. Maybe you do. Okay, so let me just say that, coin a little term here. So I'm going to say that a valuation ring is discrete if its corresponding valuation is discrete. Right? We said what does it mean to have a discrete valuation? That's a valuation whose image is isomorphic to Z. And valuation rings, there is a way of taking a valuation, or more precisely a congruence class of valuation, to a valuation ring. And note that if any of the valuations in the congruence class is discrete, then all of them are, because that's the definition of being equivalent valuations. You have there is it's not the definition, it's a theorem that we show. We show that it means that if one of them is discrete, then the other are discrete, because one is obtained by the other by composing it with some order preserving group homomorphism, namely multiplying by 5 or 2 or whatever. We called it lambda in those slides. So, once our valuation is discrete, all of the congruence class is discrete. So it makes sense to say when this evaluation class is discrete, an evaluation ring is discrete if it corresponds to a evaluation class which is discrete. Okay? So with this, we have the following lemma. Let's say you have two discrete valuation rings, O1 and O2, and with the same fraction field. Then what I'm saying is that if O1 is a subset of the other, then it has to be equal to it. And in particular, that implies that, or is equivalent to saying that the valuations are equivalent as valuations. Right, this is in a sense kind of saying that valuation rings, at least discrete valuation rings, are kind of big. You cannot, or they don't have a hierarchy. I mean, all of them are at the same level. No one is contained in the other unless it's already equal to it. We will see other senses in which valuation rings are big, but that's one. Okay, so let's prove this lemma. This lemma will be used in step 1 that we'll see later. And in order to prove the lemma, we need to prove a claim. It's essentially a trivial claim, but it's better to kind of put it aside and then go to prove the lemma. So the claim says the following. It says that, let's say you have two valuation rings with a fraction field f, then the following three properties are equivalent. First is the property that appears here, like one of the rings is a subset of the other. Second, which is actually immediately equivalent to 1, it's just a way of writing it more explicitly, is saying that for every element in the field, if V1 of A is larger or equal than 0, then also V2 of A. Right, this is equivalent to 2 because an element is in O1 exactly when this holds, right? And an element in O2 is exactly when this holds. So 1 and 2 are equivalent. We just wrote the definition of what does it mean to be in O1 with respect to V1. Now, the third property looks almost like it's a typo. It says that, I copied this line and I changed the inequalities to strict inequalities, but I also flipped the indices, right? Which does look like a typo, but it's not because there is a for every A in F quantifier. So we'll see. So we just want to prove that 2 is equivalent to 3 and then we are done. Okay, so that's what I said. 1 and 2 are equivalent in a straightforward manner. What about 2 and 3? So what does 2 mean? So 2, the way it's written, right, and going back, for every A in F, V1 of A is larger or equal than 0, imply V2 of A is larger or equal than 0. So first of all, just don't consider the element A equals 0 because, for A equals 0, the valuations are infinity and everything holds like vacuously. So if I'm going to take property 2 and consider every element A in F star, I can also consider consider the inverses of those elements, which are the same. As I said, it's the same set. So what I'm saying is 2 implies, or is equivalent to, saying that for every A in a non-zero element in the field, the valuation of A inverse is larger or equal than 0 implies the valuation, according to the second valuation of A inverse is larger or equal than 0. Right? Just because when you go over all elements here with inverses, it's the same thing as just going over all elements like that. But the reason I write it like that is because now you can just take the -1 outside of the valuation. That's one of the properties that we've seen. So this is equivalent to saying that the minus V1 of A evaluation is non-negative implies the minus V2 evaluation is non-negative. And just like moving things the other side, you can see that this is equivalent to saying that for every non-zero element, if V1 of A is smaller or equal than 0, then also V2 of A is non-positive. But you can take the contrapositive of that. Instead of saying it like that, you can say, well, for every A in F star, V2 of A is larger than 0, right? The negation of that implies V1 of A is larger than 0. And that's exactly property 3. And every step that we did was just, equivalence. So 2 is indeed equivalent to 3, and we just proved this claim. Just a minor little thing. Of course, with our days, like for a particular A, this is not the case, but for all AGCs. Okay, so with this, we're ready to prove lemma 2. So recall, we are going to assume that A1 is a subset of A2, and we want to prove that they're actually equal. And so it suffices to prove that, of course, if an element in O2 is also in O1, namely, it suffices to prove that this holds, like if V2 of A is non-negative, then also V1 of A. And it's not clear how to do it. I mean, initially, I don't know, you need a trick, and that trick kind of reappears again and again. So what we are going to do is the following. So we're going to take an element in the field, a non-zero element, like a non-zero element that's important, such that it has according to the V2 valuation, it has a positive valuation. Okay, and you can ask yourself why such B exists. And the answer would be that that's because the valuation is non-trivial. It's non-trivial because we said it's a discrete valuation. So the image of V2 is isomorphic to Z. And so it means that you can find an element with a non-zero valuation. If it's positive, you're happy. If not, you can take its inverse and it will be positive. Okay. That's just one example to argue that such B exists. But what should you do with this B? I mean, you don't care about B, you care about this A. So the idea is the following. So for a parameter M that we will kind of fix later on, let's consider the element A to the M times B. So according to V2, the valuation of this element is, just using the product rule, is M times the valuation of A plus the valuation of B. And that's going to be a strictly positive number, right? Because the V2 of B is positive, strictly positive, and V2 of A is non-negative. So for every M that we will choose later, for every M we will choose later on, but for every M that we are going to choose, this thing at the very least is going to be strictly positive, right? Okay, but so what happened here? So we just proved that regardless of what M is, this has a strictly positive valuation. And by the claim that we just proved, and because O1, by the hypothesis, O1 is a subset of O2, it means that this element has a strictly positive valuation also according to V1. Right, that's this thing. Right, so we know that per assumption. We just prove that for that element, you have V2 has a positive, strictly positive valuation. And so according to V1, it has a strictly positive valuation. So that's what's written here. So I'm not using that to prove this. I'm just saying that this follows from that and that. Okay, good. So, but now when you do open this thing up, maybe it would have been better to put it on this side. So when you do open this up, you see that this valuation is M times V1 of A plus V1 of B. And since this holds for every M, it must be the case that V1 of A is non-negative, which is what we want to prove, right? Because if V1 of A was negative, then for a large enough M, this will be negative, right? Because this is just some fixed number independent of M. It depends on B. I mean, we chose B according to V2, and now we evaluate B according to V1, but just some number. It is independent of M. B was chosen before we talked about any M's. So that's just a number. And V1 of A, if it's a negative, which I want to prove it's not, then as I take M larger and larger, in particular, I need to be like V1 of B in absolute value, then that would be negative, which is a contradiction to it being positive. And the only way around it is to make sure that V1 of A is non-negative. And that proves the claim, a dilemma. Okay. So let's see what we just proved is this little lemma that it's actually kind of insightful. I mean, you prove something about the maximality of valuation rings by arguing about the valuations and not working with the valuation rings themselves. Of course, you could have, and then you would have to kind of consider the maximal ideals and so forth. But you see, that's a very clean proof, like just kind of arithmetic proof, not ring theoretic in a sense. So with that, we are ready to kind of start proving the Artin's approximation theorem. So I mean, you could have considered that as part of the proof, maybe, but let's consider the following as the fourth step. So this is step one. And the fourth claim here is the following. So you have n valuations, discrete, so they don't have to be onto Z, but they have to be, the images have to be isomorphic to Z, and they are non-equivalent, okay? I mean, if they are equivalent, you can't say anything about their being different because they're essentially the same. Then what I claim is, at the very least, there is an element in the field that according to V1 has a 0, or at least doesn't have a pole, and according to any of the other VIs, it has a pole. Right? So you can kind of cook up an element that's defined at the point that is abstracted by V1, but is undefined by the other points, at the other points. So you see, it's kind of an interpolation argument here. Right, for example, let me just try to see if I'm not going to mess it up. So for example, if you have the point 0 and the point 1 and the point 2, these are like points on like the real line or whatever, and you want to find a function that is defined at 0 and it's not defined at 1 and 2, then you can do something like this, right? I guess this is one example that you can do. This is not defined at 1, it's not defined at 2, but it is defined at 0. So the point about valuation is that for us, they will correspond to points on a curve. And first of all, a curve has, it lives in some ambient space, which is more than one-dimensional. So you have these x's and y's floating around. But not only that, x's and y floating around also on the plane, and that's actually easier. But on a curve, there is an algebraic dependencies between the x's and the y's. So it's not obvious, and it's not generally true that you can interpolate however you want, right? If you write 1 over x, it has some implications to what happens to y, because maybe x squared plus x equals y, and so forth. So it's actually kind of remarkable that you can do interpolation, not just because it's abstract, but actually because of the algebraic dependencies that you have. And indeed, looking ahead, at some point we are going to prove the Riemann-Roch theorem, and that's going to heavily use the Artin's approximation theorem, as well as other stuff. And that, in a sense, is a kind of the accumulation point of how can you do interpolation over a curve. But Artin's approximation theorem is used not only for that, but as a step towards proving Riemann's Roch theorem, and this little claim is a good starting point, right? It tells you that at the very least, you can cook up a function that is defined at a given point and it's not defined in the other ones. Okay, so let's continue with that. Okay, so the proof is going to be by induction on n. When n equals 1, you can, there's nothing to do. You can take whatever, say x equals 0, that's fine. Its valuation is infinity, and you don't have these requirements because n equals 1. So for n equals 2, since v1 and v2 are not equivalent per assumption, we have that the valuation rings are different. That's the definition of, well, it's essentially the definition of valuation ring. It's not a definition, but a valuation ring, if you recall, we proved that there is a bijection between congruence classes of valuations and valuation rings. So the fact that these two don't sit at the same class is equivalent to these two valuation rings not being equal. But the fact that they are not equal usually won't mean much. It may be the case that one of them is contained in the other, but that's not the case, because according to lemma 2, we just proved that this means that it cannot be the case that one of them is contained in the other. Particularly, the OV1 is not contained in OV2, right? Because if it was contained, this would have been equality. It's a special property of valuation rings. So what does it mean? It means that you can find an element in OV1 which is not in OV2, right? Because it's not a subset of it. And that's it, right? Because, I mean, for the induction basis, because, well, for the case n equals 2 at least, because you just found an element which is here and not here, namely the valuation according to V1 is non-negative, and the valuation according to V2 is strictly negative, because not being in OV2 means that V2 of that element is negative. Good. So let's move along and do the induction step. And here again, you will have the same kind of M trick. So we'll see. So let's assume by induction that we found a Y, induction on N, right? So we found a Y, an element in the field, that such that V1 of Y is non-negative. So Y is defined at the point 1, but Y is a pole of all the other valuations, right? So to speak. So Vy of Y is negative for I equal 2 up to N minus 1, not N up to N minus 1. So what about the nth point, nth valuation? So using the n equals 2 case, just considering V1 and Vn, completely skipping 2 up to N minus 1, we just proved that basis anyhow. So there exists an element Z in the field that is a 0 of V1, or this non-pole of V1, and it's a pole of Vn, right? And now you somehow want to take this Y and Z. So Y works well for the valuations 1 up to N minus 1, but not N. And Z works well to the valuation 1 and N, but not 2 to the N minus 1, up to N minus 1. And you kind of want to cook up an element that works for all of them. And turns out the right way of doing that is this way. So you may try Y plus Z or Y times Z, stuff like that, but the right way is this thing. So let's consider an element which is Y plus Z to the M for some M that will be chosen later on, but definitely M is going to be non-negative, like at least one. Okay, so what can we say about this element? So before talking about this element, let's just look at Z to the M. So for I, which is larger or equivalent to, okay? Oh, sorry. So I'm going to, throughout this short proof, I'm going to throw more and more constraints, requirement about M, and this is the fourth requirement I want to take. So I'm going to choose M in such a way that Vi of Zm for every I that's larger or equivalent to, so Vi of Zm, I need it to be not equal to Vi of Y. Why do I want that? I want that because in a second I'm going to consider the evaluation of this, and I want it to use the strict triangle inequality, and I can only do that if this and that valuations are different. So I really want to choose M such that Vi of Z to the M is not equal to Vi of Y. Okay? And that's doable, right? Because, well, let's see. So what is Vi of Z to the M? It's M times Vi of Z. And if Vi of Z is non-zero, then I can certainly make sure, one can certainly choose M such that M is not equal to Vi of Y, like divided by Vi of Z, right? And if Vi of Z is 0, I mean, you see, I chose Z according to V1 and Vn. I don't know how it plays with the VIs for I equals 2 up to N minus 1. But I don't care. I'm just saying that if Vi of Z is non-zero, I'm going to kind of make sure M evade all of the values for which M of Vi of Z equals to Vi of Y. And when I is such that Vi of Z is 0, I don't care. Okay. Yeah. You can also say it a bit differently, but let's quickly that. Okay, so that's the constraint. You have like n minus 1 constraints on M at most, and that's fine. M is an integer, a non-negative number. You have plenty of those. Okay, so with this, what can we say? So actually, I'm looking at the valuation V1 for a second, so maybe kind of ignoring that. So V1 of X is, well, X is this thing. So it's the V1 of Y plus Z to the M. And by the strict, by the non-strict like triangle inequality, this is at least the minimum between V1 of I, V1 of Y, which recall is non-negative, and M times V1 of Z, which, where is it? M times V1 of Z. I want to say it's also non-negative, but I don't see v1 of z anywhere. Oh, yeah, sorry. v1 of z is also non-negative, and m is non-negative, so also m times v1 of z is non-negative, and so the minimum of these two is non-negative. So v1 of x is non-negative, that's what we wanted, right? If you recall going backwards, you want this to happen. But you want vi of x to be negative for the other valuation, so let's see that. Taking this into consideration now. Yeah, so here in this slide, I'm worrying about I that goes from 2 up to n minus 1. I want to show the valuation is negative. And then in the next slide, I'm going to consider the nth valuation. Okay? So let's go up and consider these valuations. So vi of y plus z to the m is, again, the minimum between vi of y and m times vi of z. But recall that vi of y for those i's is negative. Right? If you go back, that's the way we chose y using the induction to one-step induction backwards, so in -1. So this is strictly negative. And now if vi of z, now consider two cases. If vi of z is 0, which you recall was a problem when we kind of chose the m's before, then when this is 0, and so by the strict triangle inequality, this inequality actually becomes an equality. So you get the minimum between a strictly negative number and a 0. So it's equality, and that's a strictly negative number, which is what we wanted. And if on the other end, vi of z is not 0, then because of the way we chose m, we know that vi of y is not m times vi of z. That's here, if you remember. So the way we chose m was to evade that equality to hold. And so again, you can use the strict triangle inequality because you have this, even though this is not 0 anymore, you have this inequality. So this inequality becomes an equality. So the valuation, the ith valuation on x is the minimum between these two. Vi of y is strictly negative. So the minimum is strictly negative. Okay. Now, what about the nth valuation? So now let's consider Vn of x. So again, by the triangle inequality, it is the minimum between this and that. But we know, I mean, z was chosen according to v1 and vn. And we know that vn of z is strictly smaller than 0. And because of that, I'm going to add another constraint about m. We know that we can make, because this is strictly smaller than 0, we know that by taking m large enough, we can make this value smaller than all of these values. Right? These are just fixed values as far as m is concerned. So we can choose m large enough on top of the previous constraints that we had. We can choose m large enough so to make this strictly smaller than that. That would make this inequality to an equality. And therefore, the nth valuation on x is the minimum between two things, one of which is negative. Actually, you can make also the other, but the minimum is enough, so that's strictly smaller than 0, and you're done. I think there should be like a thing here. Good. So just to recap, what we just proved is claim 4, which means that if you give me discrete non-equivalent valuations, not necessarily onto z, you can always find an element in the field, one of which is that element according to the first point is defined. It has no pole, and according to the other valuation of points has a pole. And then if you think about the way the way this element looks like, it's kind of somewhat complicated, right? I mean, this came from the induction and this came from induction. So you took something from induction and something from the induction, and you looked at the values, and that allowed you to choose an m which is large enough. And then that's going to be a y in the next step and so forth. So that's a kind of a complicated expression at the end. But, it's fine. Okay, so now we're ready for step 2. And in step 2, we're just going backwards, we are just going to remove this equality sign, making sure that we have this forced valuation condition with strict inequality. Okay, so it's the same thing really, in terms of, it looks a very similar statement. If you give me discrete non-equivalent valuations, again, not necessarily onto Z, you can always find an element which has a zero according to the forced valuation and poles on the other. And of course, the idea would be to somehow try to use the forced claim 4, and then kind of adjust it to make a zero. So let's see how this works. So by claim 4, we can find an element, let's call it Z, we call it X, but I want X to be the final element, in the field for which V1 of Z is non-negative and the other VIs are negative, okay? And now, what I'm going to do is to take an element in the field that has a strictly positive valuation according to V1, so Y has a 0 at V1, right? You kind of want that, you want to cook according to Z and Y something. And indeed, X is going to be defined to be Z to the M times Y, again, with the same trick for M which is large enough, okay? So what do you know about X? So let's see all the valuations. So V1 of X is by the product rule is M times V1 of Z plus V1 of Y. And this is strictly positive, right? Because V1 of Y is strictly positive, and V1 of Z is, it could be 0. If it's strictly positive, we're actually done. You can, if you want, you can assume it's 0, but at least it's not negative. So multiplying by M, which is at least 1, won't hurt us. And this is larger than 0, strictly larger because of V1, really. And for the other i's, well, Vi of Z to the M times Y is, again, M times Vi of Z plus Vi of Y, but you can always make sure that it's strictly smaller than 0. Right? Because, I mean, I don't know what is Vi of Y, because Y was chosen just according to V1. I have no idea. But, you have just a bunch of numbers, like n minus 1 numbers here, and Vi of Z is negative for every such I that's not 1. So by taking M large enough, like the absolute value of this thing, or maybe one more if you want, you can make sure that these are negative. All of these numbers are negative. Yeah, and that's it, of course, because according to the forced valuation, you got strict inequality, and according to the other valuation, you got the usual reverse direction strict inequality. The important thing here is that you have strict inequality and rather than the equality from before. Okay. So step 3. So in this step, we are going to prove kind of something a bit different. So, I mean, using what we did before. So now let's say you have these n evaluations, non-equivalent. Again, not necessarily onto. Then what I claim is that there are, and you are given n prescribed valuation values as before, or at least bounds on values as before. And what I claim is that, regardless of the n valuations and for any n such values, there is a field element for which X, it's not that the valuation, not that V1 of X is large, it's that the valuation of X minus 1 is large, right? If you look at the previous lamb, it was all kind of like minus 0. It was all about the valuation of X itself, or if you want, the valuation of X minus 0. Here it's about the valuation of X minus 1, and here you still have the valuation of X's. So intuitively, kind of what's going on here is that you're saying that according to the V1 metric, X is close to 1. I mean, at least if M1 is a large number, X is close to 1. But according to the other metrics that you get, X is close to 0. Okay. And this is a bit kind of a tricky proof. So what we're going to do is the following. So first of all, by claim 5, we are going to find an element, the claim from before, that such that V1 of Y is strictly positive and the VI of the Y's for the other I's is strictly negative. That's what we just did before, ignoring this one. And now we kind of want to move things around a little bit, right? So again, for an M larger or equal than 1 to be chosen later, right, so for for m that will short tether, what I'm claiming is that, no matter how you take this m, v1 of 1 plus y to the m is 0. Right? This is because, it follows by the strict triangle inequality. But the way to think about it is that, y has a 0 at the point 1 because of that. And so y to the m also has a 0 there. And so 1 plus y to the m doesn't have a 0 there. The function 1 plus y to the m at this point should be 1. But you can see it by using the triangle inequality because, this thing is at least the minimum between the first valuation at 1 and the first valuation at y to the m. But the valuation, of course, of 1 is 0. 1 has no zeros and no pods. And this thing is positive because it's m times the valuation of y. That's positive. And these two valuations are distinct, a positive one and a 0 one. And so you can actually fix that to get an inequality according to the strict triangle inequality. And so you get a 0. So that's the proof of what I said. But at intuitive level, you can think of this as a function that vanishes at 0. And so this doesn't vanish at 0, right? Anyhow, let me just erase that. And that's all for every m. But what about the other line? So vi of 1 plus y to the m. Well, so we know that the valuation of y at the other i's is negative. So that's what's written here. So, like using the same logic, y to the m has a pole at the point I. And 1 plus a function that has a pole still has a pole. So that should also be negative. But again, you can do it with the strict triangle inequality, right? It's the same thing. You can say, well, vi, not 1, of 1 plus y to the m is at least is going to be an equality in a second, but you don't know that yet. So it's the minimum between vi of 1 and vi of y to the m. But the point is, the difference here that now this thing is negative, right, because of that. And indeed, that becomes an equality because of this triangle inequality, because this is 0. And so that is indeed negative. Right? But you can just stay with the formality. You kind of want to understand what's going on, so things will be clearer for you. So, okay. Anyhow, so we're going to choose m larger or equal to 1 such that, for every m, this holds, but we're going to choose m later on. So this is just a recap of what we just did. And now what we are going to do is we're going to look at this element, x, which is 1 over the element from before. So why are we doing that? Because let's look at x minus 1 and at x. We want to say something about the first valuation at x minus 1 and about the other valuations at x. So v1 of x minus 1, well, x minus 1 is just this expression, right? This minus 1. This minus doesn't affect anything about the valuations. Just the valuation doesn't care about minuses. Evaluations do, but valuations don't. And so just ignore that. So the valuation of this fraction is the valuation of this minus the valuation of that. But the valuation of this, v1 of that is 0, if you remember. So all of this is really just the valuation of y to the m, namely m times v1 of y. And if you remember, v1 of y is positive. And so you can choose m such that m times v1 of y is strictly larger than the prescribed value m1, right? What about the other valuations? So vi of x, well, it just minus, here it's not x minus 1, it's just x. So the 1 over becomes a minus when you work within the valuation. So it's minus the ith valuation of this denominator. And we just showed here that this thing is, well, without the minus, it's m times v1 of y. So with the minus, it's minus m times v1 of I. You see I have the wrong v here. It should be like full v. And again, because vi of y is negative for every I not equal to 1, you can make sure by choosing m large enough that, so this is a negative number, so you can make sure to choose m large enough so that this is strictly a very positive number, as positive as you would like, in particular going over the mi valuation bound that you require, and that proves the claim. Right, and here again, you can see that the function is not so easily described, right? I mean, it's like you take whatever claim 5 threw at you, and then you look at y divided by 1 plus y to the m for some large enough m. It's kind of getting messier and messier. Okay, so now comes step 4. Step 4 is kind of very similar to what you want to prove. The actual proof that we want is exactly what you see, but with equality here. And so this is a one step before. So let's read it again. So you're given n valuation, not necessarily not equivalent, but not necessarily onto discrete valuations, of course. And you're given n functions and n prescribed valuation bounds. And what you want to prove that is that there exists a field element such that with respect to any of the valuations, x is close to the eighth function. How close according to the nth prescribed value? Okay, so again, equality here would mean that we have proved the theorem. Let's do that. And actually, that would maybe seem like a good name for the weak approximation theorem. And the equality version maybe would be like the weak or just the strong approximation theorem or whatever. But actually, that's not the case. This theorem or this claim has no name. And the strong and the weak approximation theorem is with equality. And the strong approximation theorem that we'll see later on will guarantee that the x that you found, you can control the poles of that x. You can make sure that its poles align, if I recall correctly, at most one valuation. You can not have poles, but you can control its poles. And if I remember correctly, you can't prove it right now. You need at least Riemann's theorem or something. It's kind of more advanced, and we will need that. So, and yeah, so let's prove this thing, what you may call the seemingly weak approximation theorem. Okay. Okay, and this too is a bit kind of a roundabout way of finding this x. You know, but that's what can you do? So first of all, I'm saying that if all the AIs are 0, then you can just take x to be 0. Right? If you just want an element for which vi of x is larger than prescribed value, take 0, it has valuation infinity, everything's fine. So let's assume that's not the case. At least one of those AIs is non-zero. And once you do that, you can define the following number, otherwise it would be infinity. So a set of numbers. So for I in n, let's define tau I, and tau I is the following. So you go over all j's, in particular over all aj's, and you consider the ith valuation. So when defining tau I, you consider the ith valuation of all the elements, including j equals I, and you take the minimum. Okay? And one of them is not infinity, right? I mean, for every aj which is 0, you get infinity. But because we assume not all of them are 0, and because infinity is only assigned to a 0, to the 0 function, then every tau I is just an integer, not 0, not infinity. Okay, so we have this bunch of tau I's. Now, by claim 6, which is what we just proved, so it's this thing, okay, being close to 1 and close to 0 and so forth. By claim 6, applied n times, for every j you're going to apply it, there is some xj, you see, it looks like an interpolation in a sense. Okay, there is some xj such that the j valuation, according to the j valuation, the xj function that you just proved to exist has some prescribed lower bound on its valuation value. And that value is something that you'll see just kind of fits right into what we need. So I'm requiring that number. And again, for that xj, the ith valuation for every I, not equal to j, of xj, not xj minus 1, is the whatever prescribed valuation I'm writing here. Okay, so we're applying claim 6 n times, finding for every valuation j, vj, an element xj, such that according to that valuation, xj is close to 1, that close, in a sense, to 1. And that xj is perceived by the VIs to be close to 0 according to that amount. Okay? So what do we do with those? So now, okay, so I think that's just, I copied it from before. So our x is going to be defined as follows. So I'm going to go to back in a second, but this is x, just to kill the tension. Right, so the AIs were given to us, and we just cook these XIs, and X at the end is going to be this, inner product between them, or linear combination of the AIs according to the XIs or what have you. And we want to argue that this is the right X. So in order to do so, let's consider any particular summand in X. So going back here, so for I not equal to J, let's look at the I valuation. What does it say about this summand, right? So what do you know about VI of AJ XJ? So of course, it's just by the product rule, VI of AJ plus VI of XJ. And right, so VI of AJ, or maybe VI of XJ is exactly, I mean, we know that it's at least MI minus tau I. That's because of the way we define the XJs. And tau I, if you remember, was defined as the minimum here, where you go over all possible j's, and you take the I valuation on the AJ. And this is just one of these elements that compete for the minimum, right? So the minimum is smaller or equal than that number, so tau I is smaller or equal than that. And this is strictly larger than that. So you get that the J summand here of X, according to VI, is strictly larger than MI, which kind of hints about why we chose this prescribed value when we applied the previous claim. Okay, so with that in mind, let's look at X minus AI, right? Because that's what we kind of want, things like that. So X minus AI, let's write it as X minus AI xi, like add and subtract, plus AI xi minus AI. I do this because this expression is precisely, because of the definition of X, is precisely summing over all the AJ xj's for j not equal to I, right? We're working with some fixed I at this point. Well, plus here, I'm doing something incredibly smart. I'm taking A out from the brackets, but this allows me to kind of see the xi minus 1, right? Okay, so what can you say about this thing? So VI of this expression, just by the product rule, is VI of AI plus VI of xi minus 1. VI of AI is at least tau I, again, because tau I was the minimum of VI over all AJs, in particular AI. So I is one of the participants in this competition who's the minimum. So VI of AI is at least tau I, and VI of xi minus 1 is at least mi minus tau I, right? That's what's written here with j's, but think of them as i's. And so this is equal to mi, so it's a little typo here, but it shows you that VI of this thing is at least, I mean, strictly larger than mi, right? And that concludes actually that VI of x minus AI is strictly larger than mi, because we just proved that VI of this is strictly larger than mi, and VI of this is also strictly larger than mi, because according to this line, every sum in this sum is strictly larger. The valuation of that sum is strictly larger than mi. So by the triangle inequality, not the strict version, just the triangle inequality, you get this strict inequality, which is what we wanted. Okay, so we are finally in a position to prove theorem 1. And let me just remind you what the theorem is. It was a long time ago. Yeah. So now when, as I said, that's the only time we are going to use the fact that you get onto valuations. But so if you take any n non-equivalent valuations that are onto Z, and for any n, for every tuple of numbers, functions and numbers, you can find an element like a function such that with respect to any of the valuation, it's close to the corresponding function with the precise amount that you wanted. And of course, you need this to be onto, because you cannot attain a value of evaluation if that value is not in the range, right? But so far, it was only inequalities, so we didn't need that. And we almost proved that. We know this thing, so we just need to make sure to have this with equality. So you kind of expect how the proof might look like, right? I mean, you want to find also an element that has equality and somehow take those elements like for every evaluation and cook up something that works well for everything. And indeed, that's true. So what we're going to do, so by claim 7, which is just what we just proved now, with the inequality, by claim 7, there is a function y, let's call it. Let's keep x for the end. There is a y, such that for the ith valuation, it has this property that vi of y minus the given ai is strictly larger than mi. Okay, but now let's fix it. So for every I in n, let's take bi, a function whose valuation, according to the ith valuation, is exactly mi, and here we use the fact that the range is z. And we are going to now apply kind of ingeniously claim 7, this claim that we just did again, but now not for the AIs, but rather for the BIs. Okay, so again, in this line, what we did was to find one function that is very close, like closer than you may have wanted, to the AIs. And for every such I, you kind of want a function bi that's exactly close to it, like with the exact prescribed mi. So now you got these bi's and y on the side, so forget about y. You have these bi's, and now I'm going to find a function z that, according to the ith valuation, is more than mi close to the bi, okay? Not the ai. And with that, now we have this y and the z, and with that, I'm going to define the final x to be y plus z. Okay, so let's see. So what is x minus ai? So you can write it as, well, it is y plus z minus ai, but you can write it as y minus ai plus z minus bi plus bi. Right? I just added and subtracted bi and put the parentheses in places where it will be more easy to see what happens. And what I'm claiming is that vi of x minus ai is precisely mi. So why? So by the strict, by the triangle inequality, I should have an inequality here, but you will see in a second that that's an equality. By the triangle inequality, this is at least the minimum, because of the way we wrote it like that, between the ith valuation of this expression, and that expression, right? Now, the ith valuation of y minus ai is strictly larger than mi. The ith valuation of z minus bi is, again, strictly larger than mi. And the ith valuation of bi is precisely mi. So altogether, you can actually do apply the strict triangle inequality, because the valuation of this is strictly smaller than those. That's enough. So you get equality, and the equality is to the minimum, which is mi, which proves the theorem. Okay, good. Right. So I may do it also in future lectures. I will have to skip some of the proofs that I want to give, just because of time constraint. Really, the material is for a full year, not for one semester. And so in some cases, I may just ask you to read it in the notes or whatever. But when it is important enough or difficult enough, wasn't difficult, but it was important enough, then I may add these kind of appendix videos for you to see.